Okay, so this probably all needs to be copied down into your notes. But you guys remember polar coordinates from Calculus 2. And so we had these formulas for if you were given some kind of equation or if you were given points in the plane in terms of x and y rectangular coordinates. This is how you would find the r and the theta polar coordinates. And then if you were given r and theta polar coordinates, this is how you'd find the x and y rectangular coordinates. So these are the conversion formulas that you need to have memorized. You probably already have them memorized. But what we talked about yesterday is how double integrals can calculate the volume of 3D solids. If I give you a surface in space and I say, what's the volume between that surface and the xy plane? You just take the double integral of the surface to calculate that volume. But if that volume, I guess what I'm saying is, if that surface happens to have radial symmetry about the origin, and the domain, or the region in the xy plane that you want to calculate the volume over, if that has radial symmetry about the origin as well, then usually the rectangular coordinates are more difficult to use. It's a little bit more difficult to work with. But as long as the symmetry of your solid is, radial symmetry about the origin, you could use polar coordinates. And that usually makes your problem a lot easier. But the weird thing about changing your coordinates when we're doing double integrals is that you would replace the dx dy at the end of your integral with r dr d theta. And that should seem kind of strange, because you're like, okay, I'm changing from x and y to r and theta. Why isn't this just dx dy equals dr d theta? Well, we have to include an extra factor of the radius, or the r variable. So I think it might be a common mistake among students to forget that, but you will not get the right answer if you forget to throw in a little extra r. So dx dy is equal to r dr d theta. I think for most problems, maybe if not all problems, it's going to make the most sense to have the order of integration be r dr d theta. I think, you could probably try to find some problems, there might even be one in the book, where it would be better to do r d theta dr, but that's a much less common case, right? So I'll just say that this is the most common, and maybe the only problems that we're going to work in this class. It would be actually a lot less common, but possible for your problem to be easier with a different order of integration. Remember, with order of integration, you should get the same answer regardless of which order you use. It's just a matter of choosing the order of integration that's going to make the problem the easiest to solve. You want to choose the most convenient order of integration. And just most of the time, this is very convenient and this is typically not convenient. I'm not saying it's never convenient, but it's typically not. Okay. So I want to try to explain to you why. Why would dx dy be equal to r dr d theta? And the first thing is, if I were looking at this circle, and I ask you about the length of the blue set, right? The length of the blue set would be the circumference of the circle. What is the circumference of the circle in terms of r?
2 pi r.
Yeah, 2 pi r. would be the total circumference of a circle. Okay, a little bit of 8th grade geometry for you. So if I wanted to find the length of this little red segment, one thing I would need to know, or one thing you might be given, is the angle here. Let me just say this angle is d theta. That's going to be what I name my angle. Just to say that this is a little tiny sliver of an angle, d theta. And if I wanted to find the length of that little line segment, it's not exactly a line, it's a little bit curved, right? It's the length of an arc of the circle. This would be some fraction of the circumference. But the fraction would be like how much is this angle out of the total angle, right? And that's sort of the total angle of a circle, 360 degrees would be the same as 2 pi. And so that fraction should be d theta over 2 pi, where d theta is the angle measure in radians. Okay? So this is the fraction of the angle the sliver takes up in my circle times the circumference of my circle. So then the 2 pi's are going to cancel each other, numerator and denominator, and the arc length here is going to be d theta times r, or I could say r d theta. That would be the length of this little arc along my circle. Does that make sense? Okay. So, what I have here is it's like a kind of like an XY plane. But what I'm showing you is rays emanating from the origin. So you can see in the light gray, these are angle measures. So this would be 0 along the x-axis, and then theta would be pi over 6 along this ray, and then theta would be pi over 3 along this ray, and then theta would be pi half along the y-axis. So these are measures of theta. And then the distance away from the origin is r, right? So this is just gridded up for polar coordinates. Now, each one of these little squares, I mean, it's not a square. It's not even really a rectangle. Each one of these little areas that looks like a rectangle, let me give that a name. I'm going to name that dA. For a little small area, and you can imagine these shrinking if the angle shrinks or if the difference in the radius shrinks. Going from like here to here, I've changed the distance from the origin. So I might call one of these little line segments dr, okay? Because it's a change in the distance away from the origin. Then one of these kinds of line segments, this is actually part of an arc around a circle. And so the formula for the length of an arc around a circle is r d theta, not just d theta. D theta is the change in the angle measure, but the length of this little arc segment is r d theta. So what that's saying is if you wanted to calculate one of these areas, if you wanted to calculate one of these dAs, we would say that dA is dr times r d theta. Or we could say that dA is r dr d theta. Back when we were doing rectangular coordinates where we had x's and y's, in rectangular coordinates, we could get a little area just by multiplying a little change in my x direction times a little change in my y direction, and that gave me a little differential area packet. But in terms of the polar coordinates, just dr times d theta would not be an area. But r dr d theta does give me one of these little differential areas. Okay. So here's an example. What if we want to find the volume of a solid that is entirely inside this sphere and also lies inside this cylinder? So let me graph this. We've got x squared plus y squared equals 4. So that's the cylinder. I'm saying my solid has to lie inside that cylinder. And then also, this particular solid we're talking about has to lie inside this sphere right there. So, change one of these colors. Okay, so inside the blue sphere and inside the red cylinder is going to give me the shape that's mostly cylindrical, but it's also going to be kind of rounded on the tops and the bottom, well, the top and the bottom, right? It does have radial symmetry, right? So we were talking about how polar coordinates would only really be useful if the volume of the solid you're talking about has radial symmetry around the origin. And yeah, it looks like, you know, the domain or the area in the xy plane has radial symmetry about the origin. And the top of it, which is the surface of the sphere, it also sort of has the same sort of radial symmetry. So it seems like polar coordinates would be a good candidate for actually figuring this out, and it might be a lot more convenient than if we just use rectangular coordinates. The first step is going to be making this explicit in terms of z. And so this, I could say z is equal to the square root of 16 minus x squared minus y squared. And I also need it to be inside the cylinder. And so I'm talking about, you know, all of the volume where x squared plus, y squared is less than 4. And in fact, if I said, if I wanted to really describe this, I would say that my z-coordinate has to be less than the positive square root, because the positive square root is going to give me the top of the sphere. And then, you remember if I take a double integral, that gives me the volume between the plane and the surface? In this case, the surface is the top of the sphere. I could then get the volume of this whole solid just by multiplying by 2. Because if I use the xy plane to slice it in half, and I just take the volume of the top, well, the bottom is the same shape and the same size. So I could just multiply this volume by 2 at the end. And that's how many use what?
Asymmetric, the top and the bottom?
Yeah, right? I mean, yeah. Do you see how the sphere slices that? Or sorry, the xy plane slices the sphere in half? Yeah. Okay, so that's what I'm going to do. I'm just going to calculate the volume above the plane, because that's easy to do with a double integral, and then I'll multiply it by 2. Okay. Now I want to convert to polar, right? These are in rectangular coordinates, but I know that since it has radial symmetry, it's going to be really nice if we convert this to polar coordinates. So in this case, I would say My surface is going to be z equals the square root of 16 minus what? R squared, yeah. Because r squared is equal to x squared plus y squared. That was the first conversion formula I showed you on the previous page. And then whenever I say it has to be inside the cylinder, and I say it has to be x squared plus y squared has to be less than or equal to 4, I could instead say that r squared has to be less than 4. Or I could just say that r, since r is my radius, or I should say r is my distance from the origin, r just has to be less than 2. Okay, what about theta? Theta is the angle from my x-axis, but this solid is all the way around, right? I mean, so I can let theta go anywhere between 0 and 2 pi, right? I can let my radius be anywhere between 0 and 2, and this is going to be a good little setup for us. So we're going to set up this double integral. We're going to say the integral with respect to something, and then remember we're going to use r dr d theta. Don't forget the little extra r we get for doing polar coordinates. And since the last thing says d theta, that means the first bounds of integration are going to be the lower and upper bounds I have on my theta angle. So that's going to go from 0 to 2 pi for my outer integral. For my inner integral, I'm integrating with respect to r, and so my lower bound and my upper bound for my radius are going to be 0 and 2. And then for my integrand is going to be the surface, where we're trying to find the volume under the surface, and so that's going to be the square root of 16 minus r squared. Does everything make sense so far about this setup? Because setting it up is going to be a lot harder than solving the integral. You guys have been doing integrals for the past year, at least, but setting it up is the difficult new task we have to do. So I think to figure out the integrand, there's an easy Calculus 1 strategy we can use called, yep, perfect. A u substitution where u is equal to I think the easiest, there's probably multiple ways you could do it, but I think the easiest way is 16 minus r squared. And then if I take the derivative of that with respect to r, it gives me negative 2r. So I'm going to replace dr with negative half du. And then I'm going to write the integral from 0 to 2 pi of the integral of square root u, or I could write u to the 1/2 power instead of the square root. And then r times negative half du d theta. Now that I'm doing the substitution, I need to figure out what my lower and upper bound of integration would be in terms of u. So if I plug in r equals 0, u would be 16 minus 0 squared, so my new lower bound of integration should be 16. If I plug in r equals 2 for my upper bound, then u is equal to 16 minus 2 squared, so my new upper bound should be 12. Did that make sense? Did I make any mistakes in my u sub? Oh, sorry. Ha. I did make a mistake. That's a good catch. So this should have a little r down there, and then there should be a little r right there. That's a good catch. So this is going to be the integral from 0 to 2 pi. I'm going to take out this constant 1/2. Since that is a constant multiplying everything, I can take out the 1/2. The r's are going to cancel. And then instead of having a negative here, I don't like how the bounds of integration are 16 to 12. I would rather have my bounds of integration be 12 to 16. But you remember if you flip the upper and lower bounds of integration, you just make it negative. So I'm going to get rid of the negative and then flip my bounds of integration. And then this is going to be u to the 1/2 power
Is that allowed to do?
du d theta. Yeah. Yeah, you didn't know that?
No.
Okay. Sometimes I mention this to my Calculus 1 students and sometimes I don't. But if you have the integral from a to b of f of x dx, this is the equal of negative b to a f of x dx. If you think about it, what you're going to do is you're going to take the antiderivative, because this is equal to the antiderivative of that function evaluated at b minus the antiderivative of that function evaluated at a. And that would be the same thing as negative antiderivative of a minus antiderivative of b. Yeah, so does that make sense?
Yeah.
There, okay. So that's what I did. And now I have to take the antiderivative of u to the 1/2 power. And so the power rule tells me that this would be, let's see, 1/2 integral 0 to 2 pi of u to the power 3/2, and then I would have to multiply everything by 2/3. And then I want to evaluate that at 16 and at 12, and then subtract, and then d theta. So this is now 1/3 and integral 0 to 2 pi. So it's going to be 64. Ooh, and then that gets ugly. Ugh. Okay, so if I plug in the 16, then the square root of 16 is 4, and 4 cubed is 64. So that's the upper bound part. The lower bound part is the square root of 12 cubed. And that's not very nice.
Maybe 24 root 3.
24 root 3. Probably. Yeah, because it would be like 2 times root 3 all cubed, so it would be 8 times 3 times root 3. Yeah. 24 root 3. There's no thetas here. So integrating with respect to theta is going to be really easy. We would just take the antiderivative and multiply the whole thing by theta, and then we plug in 0, and that would make the whole thing 0. Or plug in 2 pi, and that just means we multiply everything by 2 pi. So this is going to be 2 pi over 3 times 64 minus 24 root 3. So it's not going to be a very nice answer. I can't even take 64 divided by 3. That's not even very nice. Right? It's not divisible by 3. So that's good enough. Clearly y'all realize that's some number. My pen. There you go. Cool. Any questions about how we did this problem? Oh, and that's just the top half, right? So if I wanted the volume of the whole thing, don't forget to be like, oh yeah, I have to multiply by 2 because then you've got the top half and then you've got the bottom half of the solid. Okay. Next example. It says evaluate the following integral. So I've got a nice double integral, where R, the region that we're integrating over, is the annulus. So the annulus means that it's the space in between these circles. I'm not counting the space inside the inner circle. I'm not counting the space outside the outer circle, but the annulus is all of this region. So this region would be really difficult. I mean, I think it would be really, really difficult to describe using rectangular coordinates, x and y. But this region is really easy to describe using polar coordinates. How would I describe this using polar coordinates? R is the distance from the origin, right? So if I wanted to describe to you all of the points that lie in this region, in the annulus, I would say that R has to be less than 3, right? Because the radius of my big circle is 3, but it has to be greater than 1. Yeah, exactly. So this double inequality right here, that describes that annular space in polar coordinates. And of course, theta can be anything because this has radial symmetry all the way around from 0 up to 2 pi. Then I remember that my conversion formula for x is r cosine theta. My conversion formula for y is r sine theta. And I've got x squared there in the integrand, but x squared would just be r squared cosine squared theta. So if I want to set up my double integral, this is going to be the integral where I've got r d theta at the end. Don't forget your extra r. Theta can be allowed to be anywhere between 0 and 2 pi. R is allowed to be anything between 1 and 3. And then my integrand is going to be x squared plus y. So that's going to be r squared cosine squared theta plus r sine theta for my integrand. All of that times another r, dr d theta. So let me distribute in my extra r. And just rewrite this real quick. I could rewrite it as r cubed cosine squared theta plus r squared sine theta dr d theta. And then for the inside integral, all I have to do is take the antiderivative with respect to r. So I'm treating theta as a constant, which means I can treat cosine squared theta as a constant. I can treat sine theta as a constant. And then all I have to worry about for right now is the antiderivative power rule. And so this would become r to the 4th over 4 cosine squared theta plus r to the 3rd over 3 sine theta. And I'm letting r be either 3 or 1. So I'll have to plug those in. If r is 3, then 3 to the 3rd power is going to be 81. So I have 81/4 cosine squared theta. Yeah, right here?
Oh, no, I think you said R2 to the 3rd or something.
Oh, sorry, I misspoke. Well, 3 to the 4th power is 81, right? So at least I wrote the right thing. So I have 81 over 4 cosine squared theta. And then plus 3 to the 3rd power would be 27. Of course, divided by 3 is easy. So 27 divided by 3 is 9 sine theta minus 1/4 cosine squared theta minus 1/3 sine theta d theta. Okay, now I have to think about how I would take the antiderivative of cosine squared, and the antiderivative of cosine squared is going to be not fun. So instead I'm going to use this trig identity, the trig identity that says cosine squared is equal to 1/2 1 plus cosine 2 theta. So I could write 81/4 minus 1/4 would be 84, which would be 20 times cosine squared, which is 20 times 1/2 1 plus cosine 2 theta, plus 9 is the same thing as 27/3. 27/3 minus 1/3 is 26/3. So I'll say plus 26/3 sine theta d theta. Now I think we're ready to go ahead and take the antiderivative. So this is going to be 10 plus 10. Antiderivative of cosine would be sine of 2 theta, and then I would have to divide by 2. So 10 divided by 2 is 5. And then the antiderivative of sine would be negative cosine. So I'll have negative 26 over 3 cosine theta. And then my bounds of integration were 0 and 2 pi. Now sine of 0 is 0. Sine of 2 pi, oh, I should say sine of 4 pi is also 0. So I actually don't care about this term at all, because the sine's always going to be 0. Ooh, and I made a little mistake. That should be 10 times theta. Ooh, so sneak in a little theta there. Because it's a constant here in my integrand, so when I take the antiderivative, I need to add a theta to it. So 10 times 0 would be 0, but 10 times 2 pi would be 20 pi. Cosine of 0 is 1. Cosine of 2 pi is also 1. So it would be 2 pi minus 26/3. Yeah, good catch. So you're right. So cosine at either bound is 1. Cosine 2 pi is 1. Cosine 0 is 1. So that'd be 26 over 3 minus 26 over 3. And that would cancel itself out. So now I just have 20 pi.